Hi everyone. Just a note, we have started recording there. So the first session is going to be a talk by Professor Claire Gormley from UCD in the School of Maths and Stats there. So where she conducts research in statistics and she also teaches statistics in the school. She is the co-director of SFI's Centre for Research Training in Foundations of Data Science, as well as a PI in the Vista Milk Research Centre in UCD and a funded investigator in the Insight Centre for Data Analytics in UCD. Her research develops novel statistical methods, largely based on latent variable models for the analysis of high-dimensional data, and often of a mixed type. These methods are often motivated by solving applied problems across a range of disciplines, including epigenetics, metabolomics, genomics, social science, sports science, and political science. So today she's here to talk to us about the Bayesian nonparametric modeling of network data. So I'll hand over to you now, Claire, and we're excited to hear your talk.
Thanks very much, Kate. Morning, everybody. I hope you can hear me okay. And I will try to share my screen. And just double check you can see it and that it moves when I move down a slide. Okay, great. So yeah, good morning, everyone. Thanks for coming, and very much thanks to the YSA and the Benoni Society for the invitation. I'm assuming I'm invited because I'm still a young statistician, so I will take that. Thank you. As introduced by Kate, what I'm going to talk today about is a Bayesian non-parametric approach to modeling network data. And largely I'm presenting the work of Zhanya Gui, who many of you on the call may know from the YISA. He's a just finished PhD student in the School of Maths and Statistics in UCD. And what I'll speak about today essentially is the work he did as a part of his PhD thesis under the supervision of Dr. Michael Fopp, who again here on the screen, who many of you may know, and myself. So very much Gui's work that I'm just presenting today. Okay, so network data can be a nebulous word at the moment. Network is taking a lot of things. So what do we mean here by network data? I'll explain it through an example. So this plot is an image of network data that comes from measurements of the connectivity in different regions of the cortex in the brain of a cat. Each colored blob here is a node or a region in that brain, and the grey lines between nodes indicate a sort of a connection in some sense between them. The different colors represent different nodes from different regions of the brain, which sometimes can be of interest. So this is network data. We have a group of nodes and we have links between them. And this is just one way of plotting the data or looking at it. This is one potential visualization that we see here. I've just thrown up on the screen 3 more. There are many possible ways of visualizing network data. There's lots of different algorithms out there that try to place the nodes on a 2D plane to present the network data. And in a sense, this is some of the ideas that motivated Gui's work. So while many of these layout algorithms are available, they literally lay out the nodes in a network. And some of the names I've listed there in the slide are probably familiar to you. The challenge then becomes, well, which one is most appropriate? Which is the one that we can use to help visualize the network data that will communicate the information contained in the network as clearly as possible. It's difficult to interpret. Very often it's difficult to interpret these sort of layout type presentations of graphs or of networks, particularly if they're very large networks. So as the number of nodes grows or the number of edges, number of connections in those networks grows, it's very difficult to convey information just from sort of a layout type algorithm to present these. And one of the challenges is that the location in that, say, 2D plot on the previous slide, the location and the distances between the nodes in those plots has no meaning. There's no sense of the measurement between those in that 2D Euclidean space having anything to do with the sort of the network properties themselves. It's purely a visualization tool. And from we're all statisticians, I'm assuming here. So from our point of view, there's no sort of dimension reduction or model-based ethos to these representations, and they're very much layout driven. And very often, because we're humans, we plot these in 2 dimensions, and we do that really simply out of convenience, because our human brains can interpret those. But there's really nothing to say that the underlying structure in many network data sets happens to be two-dimensional. So our approach is to use a statistical modeling approach to tackle some of these issues, and they'll allow us to simplify and summarize network structure, as any sort of statistical model does, but also it will give us a nice way to summarize and simplify the visual representation of networks. And importantly, as statisticians, it helps us describe and understand how the network that we've observed has been generated, where it has come from in the context of the cat brain, what is generating those connections between different regions of the cortex. And once we have a statistical model, then that opens the door to, very naturally, to model extensions and allow us to do more complicated tasks. So let's say we wanted to cluster the network nodes. Once we have a statistical model, it's much more, straightforward and arguably coherent way to do that once we have a statistical modeling underlying our network. And often of interest is predicting future interactions. So if we're modeling, telephone networks or something like that, we want to predict what may happen in the future. And once we have again a statistical model, we can do this in a robust and reproducible and principled way. Okay, so as I said, what GUI's work really focused on was developing Bayesian nonparametric models for network data, and we termed the model a latent shrinkage position model. So if you're not familiar with network modeling and you're not familiar with Bayesian nonparametrics, hopefully if you can leave this talk with at least what this slide says, which is the message of the work in a nutshell, that will be hopefully a good takeaway. So this is an example of a toy example of a network. Again, nodes are the little circles, gray lines between them. This is just one way of visualizing. We've plotted it in 2D, but there's really no necessary reason to do that. And the distances between nodes in this representation is meaningless. It's just purely a visualization tool. So what the latent shrinkage position model aims to do is to represent that network in a latent space, an unobserved space that we assume generates the network. And we allow it to have as many dimensions as it needs, essentially. So on the right here is another representation of the same network in this latent space that you'll see later how we actually infer that from the data. And here it has 3 dimensions. I've labeled them Z1, Z2, and Z3. And while it's just, again, another representation of the network, what we do have here are important properties that are useful. So the distance between the points in the latent space representation are related to the probability of having an edge between those 2 points or those 2 nodes. And as we move down the dimensions, the sort of the proportion of information that's contained in those is going to decrease. So we get this low dimensional, what is our Bayesian nonparametric approach give us? It gives us a low dimensional interpretable representation of our network in a p-dimensional space. In the left, p is 2, in the right, p is 3, and part of the task here today is to try and figure out how we can infer p. As I say, we have this nice concept in the latent space representation that the latent dimensions are ordered in a sense of importance. And because we can draw on this Bayesian nonparametric sort of machinery, it allows us actually to automatically infer p, the number of dimensions that are required. So as you'll see, in some cases that suggests that 2 dimensions is appropriate, and in other cases it suggests that p is either, if you use 2 dimensions, you're either over complicating the network representation or underestimating the complexity. So in a nutshell, that's what we do. We collapse it into a lower dimensional space where there's meaning in the location in those spaces, and we can, in a principled and automatic way, infer how many dimensions are in that latent space. Okay, so to get into the weeds of it a little more, for notation, we have a network corresponded to a graph with a set of nodes n and a set of edges e. And we're going to record the relations between those set of n nodes. Record this in a n by n adjacency matrix. So in what follows, I'll call that capital Y. And each entry, Yij, for example, is equal to 0 if there's no connection between those 2 nodes, but if it's equal to Wij if Y and J have some sort of connection. And then the value that Wij can take depends on your network. So you may have a binary network, like the cat network I showed at the start, where it's just an indicator of there is a connection between these 2 regions of the brain. It could be count network, so it could be the number of phone calls between one mobile phone and another. It can be a weighted edge. There's very many possibilities for the form of Wij here, depending on the network under study. In Gui's work, he considered binary and count network data, but for today's purposes, I'm only going to consider binary network. So in what follows here today, Wij is either a 0 or 1, indicating no connection or a connection. So we draw heavily on, I suppose, two core pieces of work. One is the latent position model, so a paper by Peter Hoff and co-authors back in I think it's in JASA, and then another paper from the Bayesian nonparametric side, which I'll speak to a little later. So Peter Hoff and co, their concept of this latent position model for network data was very simple, but has become very widely used. And essentially, they assume that there is a latent variable, here I'm going to call it capital Z, that captures the association between the nodes and essentially is this location of the nodes in this latent space. So we model the adjacency matrix Y given some parameter alpha that again I'll speak to in a minute, and this latent variable Z, and given or conditional on Zi and Zj, which is the location of node I and node J in this latent space, we can model the links between I and J as across our network as independent. So the key point here is Zi is just sort of the coordinate or the location of node I in this p-dimensional latent space. And this spawned a huge volume of work. So there were the model-based clustering approaches based on this latent position model that had this underlying latent variable. People extended it to weighted and dynamic networks, multidimensional networks, et cetera, et cetera. So it's been a very well used and well sort of explored model in the literature. How it actually models the probability of a connection between two nodes is as a function of the Euclidean distance between those two latent locations. So depending on the form of Wij, in our case it's binary, so we simply have the log odds of a probability of a link is equal to this sort of intercept term alpha, which links actually to the density of the network, and then a decreasing function of the squared Euclidean distance between node I and node J in that latent space. So again, this idea that the distance in that latent space has some meaning and influences the probability of a connection. So two nodes that are very far away, it's going to have a large square distance, and the negative effect here will give you a low probability of a link between them. And then under the hood, they make this assumption that the nodes lie on a p-dimensional latent space and that these locations follow a Gaussian distribution. So we assume Zi in that initial plot, that nutshell plot I had at the front, is a vector of length 3, so p was 3 there, assuming a Gaussian centered at 0 and with some diagonal covariance matrix, where the variance down the diagonals was the same for each of the p dimensions. And it's a really nice network model. It captures lots of sometimes difficult properties for models to capture in terms of the network literature. What P is, though, is a tricky problem. In the original papers, they tried some ways to tackle this, but most commonly people set P as 2 and just sort of run with it because we can plot it and look at it. But as I say, there's no very principled statistical way to choose it. So the challenges in selecting P, how many dimensions we need or what dimension that multivariate Gaussian is problematic. While they did use model selection criteria like BIC, for example, etc., in the original papers, they do lack theoretical justification here. If you fit these models from and then want to use something like a BIC to choose between them, it means you have to fit lots of different models because you're, which can be computationally heavy. Your model search space is huge. And importantly, as this is a Bayesian statistics morning, there's also no uncertainty then in P. If we just fix P at 2 or use BIC or something like that to choose it, there's no concept of the uncertainty in P being communicated or studied. And then further, as based on the notation in the previous slide, all dimensions are equally important. In the original position model, there was that diagonal covariance with the same variance down the diagonal, and that can be too restrictive. So our goal here was to try and identify what we call the number of effective dimensions. So if we had an infinite number of dimensions in this latent space, how many of them would contain information that influences the probability of a link between two nodes? So we're trying to identify what we call effective dimensions that have essentially non-negligible variance. So to give a picture of what happens under Guy's work, or what he proposed, which was called the latent shrinkage position model, here we have a toy example with 4 dimensions in the latent space. And you can see either by looking at the scatter plots in the upper panels, or the sort of histograms in the lower panels, what happens as we move across the dimensions. So you can see the variance of the positions is shrinking as we move across the dimensions. So there's less and less information. So for example, in dimension 4, there's very little information for us there in terms of the probability of forming edges between nodes in comparison, say, to dimensions 1 and 2. So how do we achieve that? What is in the model that allows us to shrink this variance as we move across the dimensions? And this is where we draw heavily on a paper in the Bayesian nonparametrics literature from Anirban Bhattacharya and David Johnson back in 2011, a Biometrica paper. And they proposed multiplicative gamma process prior, the MGP, and we took that and adjusted it slightly, that accounts for a truncation point to ensure shrinkage. Key idea is we assume that the latent position Z now are drawn from a Gaussian distribution, same as the original latent position model, but here it has an infinite number of dimensions. We're not going to specify P in a sense. We're just going to say, well, there are an infinite number of dimensions here with some covariance omega, and we allow omega is diagonal. Or sorry, the precision is omega. It is a diagonal matrix, but the entries vary by the dimension L. So as L moves from 1 to infinity, that variance is going to, in our case, shrink. And that shrinkage comes about by considering a product, so hence the multiplicative piece of these delta terms, or these shrinkage parameters, where they're assumed to come from gamma distributions. So as we take the product of these deltas, which are gammas, so positive, as we move across the dimensions, the omega term blows up, which means the variance, the omega is the precision, so the variance is going to shrink. So it's a very simple idea in a sense, and it works very nicely. So this sort of Bayesian nonparametric framework, because we have this infinite number of dimensions, means that if the precision at dimension L is going to be, by definition, greater than the precision at dimension L minus 1, which means your variance is shrinking as we move across the dimensions. And essentially then what we do is we look across these variances and choose the number of sort of relevant or effective dimensions to be those that have non-negligible variance. We can dig into some of the, some of the theoretical properties then of what this prior means in terms of the distances in the latent space. So in the paper, Guy has a nice section where he explores, for example, what is the expected pairwise square distance within a specific dimension. So if we take dimension L as 3, for example, how does the expected value of that square distance, given the precision for that dimension, how does that behave? And that allows us to sort of examine the influence of the hyperparameters here, A1 and A2, which were the hyperparameters of the gamma piece in the prior and the previous slide. And here, for example, are some of the things that we can look at. So here, actually, A1 is fixed to be 2 here. And what we have here on the x-axis is the number of dimensions increasing, heading off to infinity. And the y-axis is just expected pairwise square distance between node I and node J in dimension L. And then the different colors are different values or different settings of the hyperparameter A2. So you can see as the hyperparameter increases in value, so as we move from 1 to 4, you can see the shrinkage is getting heavier. So when A2 is 4, you can see we shrink very heavily. And even by the time we're at dimension 4, the expected square distance is very close to 0 already. And I think in what follows, we used A2 is equal to 3, but we did do sort of prior sensitivity analyses. And I think I'll skip this, it's in the paper, but essentially, we also looked then at, well, what's expected pairwise square distance across, not just within a dimension, but across all dimensions. You can explore the behavior of that for different values of the hyperparameters and different what we call truncation levels, because practically we actually have to truncate to sort of fit these models. So if you want more on that side of it, as I say, it's in the paper. Okay, so that's our basic idea. We make this assumption, we are in a Bayesian framework, so we put priors and parameters, we put on the shrinkage priors that sort of allow us to do automatic inference. And then we just want to sample from the joint posterior distribution of that intercept term alpha, which is like the density of the network, our latent positions Z that we want to infer. We need to infer the location of each node in the latent space, and these shrinkage parameters, the deltas, that when we take their product are going to allow us to shrink the variance over the dimensions given our adjacency matrix. So what are our priors for the Z? We just have that Gaussian distribution, mean zero and with precision omega. For the deltas, we have the multiplicative truncated gamma process prior. And here the truncated piece means from dimension 2 onwards, we truncate at 1 so that the values of the deltas have to be greater than 1, which ensures the shrinkage as it goes. And we put quite a non-informative prior on the density parameter for the intercept, just a normal 0.9. The likelihood term then depends on whether you have a binary network, a count network, a weighted network, whatever type of edge you have. So here, and today what we're going to talk about is only binary networks. So we just have this is just the product over the log odds, basically a logistic regression model for modeling the presence or absence of an edge as a decreasing function of this squared Euclidean distance between the nodes. So the usual Bayesian framework, we have our priors, we have our likelihood, we turn the handle, we get our joint posterior distribution, and then we need to do inference on it. We use an MCMC algorithm, Metropolis within a Gibbs algorithm, and again, for time reasons, I won't go into the nuts and bolts of it, but essentially it's Metropolis Hastings for the locations and for the alpha parameter, and then we can use Gibbs to update those shrinkage parameters, the little delta terms. In practice, so it's all nice in theory to say, well, we just let it have an infinite number of dimensions and then see how many of them sort of have non-negligible variance. But in practice on a computer, we actually have to set a finite number of dimensions to fit these models. So we actually need what we call the number of active dimensions, P, to be finite to practically use these. So what we do here, you can just fix it to a large value and allow the chain to run. But what we do here is use an adaptive sampler that allows that finite value that we're at least working with to increase or reduce as the chain evolves. And essentially, there's a bit hidden under the hood here, but it works by, at the start of the MCMC chain, you adapt a lot, but the probability of adaptation decreases exponentially fast as your chain evolves, and eventually you'll settle into a number of active dimensions. So for example, here, that's what the plot shows. The x-axis here, we just have the iterations as the algorithm runs. The y-axis is just the number of active dimensions, and that doesn't mean dimensions with non-negligible variance. It just means sort of the number that we're carrying around in memory, some of which, if not all of which, will have non-negligible variance. So you can see early on in the chain, it's adapting a lot. It's jumping around from having sometimes 3 dimensions, sometimes 7, and then it settles down as the chain evolves. And what this importantly allows us to do is, as Bayesians, is worry about the uncertainty in the number of dimensions P. So here, for example, from this app, after we've run our MCMC chain, we can pull out, for example, the posterior probability of the number of active dimensions. So here we can look at the number of active dimensions as the chain runs, and it gives us again this sense of uncertainty in P that we actually don't know that 2 dimensions, for example, is appropriate. We ran a good few simulation studies, all of which are detailed in the paper, but I just pulled out 2 to talk through here today. One considers the impact of different initial truncation levels. So related to the last slide, we have to start with some finite number of factors, and how does that actually affect how things run? And then what about different network densities? So if you have a very sparse network with few edges, or a very dense network where there's lots of edges, how does that affect performance of this logistic LSPM where we use we're assuming binary data? And we do a bunch of posterior predictive checking just to be, again, thorough statisticians. Okay, and I'll talk to those measures as we look at the plots, and in each case we just ran 30 replicates. So this is where we have different initial truncation levels. So P0 is going to be the number of latent dimensions that we start the chain with, where the truth here, the simulated data, is 4. So what's really the take-home message? If you look at the second one here, for example, if you start with only 2 dimensions and the truth is 4, the sampler it's difficult for it to sort of get back up to where it should be. If you start at the truth, everything is fine. You can see with most posterior probability of 4 dimensions. And interestingly, if you start with a number higher than the truth, it seems to be able to sort of drop itself back around to the region of high posterior probability. So kind of the learning from this was you're better to start with a higher number of dimensions and allow the algorithm to settle itself rather than a lower number. And then in terms of model fit, what we have here in blue is the output of the latent position model. So the Hoff et al. Version where we just fix P is 4 is finite and the same variance down the dimensions. So we can look at, say, when we draw replicate data sets from the model, we can look at the network density in those replicates, and the red line is the true density in the simulated data. The transitivity is a feature of the network. And then we can look at measures like the accuracy of predicting edges that are there, things like the F1 score or the Hamming distance, because we're dealing with binary networks here, you know, how like the observed data are the replicate data sets. So you can see, you know, in the round, everything fits quite well, but you can see there's definitely more uncertainty around things when we start at a lower truncation level. So when P0 is equal to 2 here. And then in terms of the shrinkage strength, what happens to it? So again, this is the same setting. So our truth here is 4 dimensions. And maybe just to get to the take-home message, for example, here, if you start with 10 dimensions when the truth is 4, the red X's here are the true values of the shrinkage strength, simulate the data, and you can see it estimates the 4 first dimensions well, and then you can see the variance or shrinkage parameter shoots up, which is going to blow up the precision and really shrink your variance. So in a sense, you can use these plots as a way of assisting in selecting the number of dimensions. Or perhaps it's easier to think of variance shrinking. This is the same plot, but just for the variances rather than the shrinkage parameters. And you can see what happens, you know, it'll fit the variance. It's decreasing over the first 4 dimensions, and then the variance really plummets after that. I think in the interest of time, I will jump to the second simulation study. But really all it says is that if you have different density in binary networks, here there's 3 dimensions. If you have very sparse networks, so where the empirical network density is very low, model fit isn't great. So Krusty's correlation here is between the true latent space and those generated by replicate data sets by posterior predictive checking. And you can see the model fit is poor when you have very sparse data sets. It's also not great when you have very dense data sets, but when you're in that sort of middle range of densities, the model seems to perform okay. Okay, I just wanted to get to a couple of real examples. So one is the Zachary Karate Club, which I'm sure many of you know. It's a very well-known network data set. It's a little toy one you can kind of look at. So it has 34 nodes, links or relationships in a karate club, and the density of the network is 14%. And there's knowledge about sort of there were 2 cliques in the network here indicated by the different colors. And this is one just visual representation of that network. If we fit Guy's model, latent shrinkage position model, you can see the posterior probability really indicates 2 dimensions is appropriate, which is reassuring for all of us who've plotted it in 2 dimensions for many years. But if you fit the latent position model and use the BIC, it actually suggests 1 dimension, which our approach suggests there's actually very little posterior support for. And then you get your resulting latent space plot in your 2 dimensions, but here where the distances between nodes actually mean something. And again, we can check our model fit, you know, what are our posterior predictive checks like if we compare the latent position model with the finite 1 dimension compared to our model with the nonparametric approach that essentially tells us there are 2 effective dimensions. And you can see in some ways it does well. The density and the transitivity are probably better. The accuracy is actually a bit better in the latent position model. But in the round, they perform relatively similarly. For the cat data set that I opened with, so it was the regions of the brain and the cats, it's about 27% dense, so kind of one of those nice networks. And this was a case where the latent shrinkage position model quite heavily suggested 3 dimensions were needed to reflect the complexity in this network, where again, the latent position model, the finite approach, using the BIC to select the optimal model, suggested 2. So this is the case where, we would argue that you actually do need all 3 dimensions here. So here I've just plotted 1 against 2, 1 against 3, and 2 against 3. That you need all of these 3 dimensions to sort of explain the variation in the data. And here you can see the sort of the idea. They're deliberately plotted with lots of white space because all of the axes are the same here. So you can see the shrinkage of the variance, or the shrinkage in the shortening of the distances between all of the nodes as we move across the dimensions. And again, we check all the model fit diagnostics, and it does, actually here it does much better really than the finite model with the 2 dimensions in terms of the density, accuracy, and Hamming distance. All are much improved. Hamming distance here is the opposite to the others. You're hoping for a small Hamming distance, but a high accuracy and high F1 score. In terms of runtimes, on average, for else, it's difficult. I don't really like comparing runtimes, but just to give you a ballpark, does this take days or hours? Because a lot of it just depends on code. So to fit these kinds of models, our latent shrinkage position model takes about 10 minutes on a regular laptop. Similar-ish for the latent position model, say to run with P is 5 using the latent netar package. It took about 7 minutes, but for using the finite approach to latent position model, you have to fit lots of these models, so that time is going to accumulate. And I had one other example, which was a larger network that was quite sparse, and really just to show that in this case, the BIC is quite uncertain. You could see, if you imagine you were running this with the latent position model, it's difficult to know whether it's 3 or 4 dimensions. Whereas when you take this Bayesian nonparametric approach, you get a very similar message, but we can quantify that uncertainty between whether it's 3 or 4 dimensions that are needed. And indeed, if you look at the resulting shrinkage strengths and posterior distributions, you can see over the first 3 dimensions, the shrinkage parameter is quite small, but then it blows up quite quickly in dimension 4. That really would suggest that the 3 dimensions is probably sufficient here. So that's sort of the basis. And then what a bit going back to the early point, once you have a statistical model, then sort of the world's your oyster. So once Gui had this latent shrinkage position model, then he said, well, let's cluster the nodes and you have a statistical model. So instead of assuming the latent locations come from a single Gaussian, we can now assume they come from a finite mixture, and use the well-known sort of model-based clustering infrastructure to do clustering of these nodes. We still have this shrinkage prior on the variances, but he combined this with the idea of what are called overfitted mixture models. Essentially, we fit too many clusters and allow them to empty out, akin to the shrinking variance across dimensions. And essentially, this allowed us to do automatic inference in a single model on the number of dimensions and the number of clusters that are required. Again, avoiding this idea of having to fit lots of models with different numbers of dimensions and lots of models with different numbers of clusters, and then trying to choose between them. And we looked at a very nice toy example where we looked at Twitter mentions between players in the English Premier League. It's a very small network with about 55 players, and again, a nice density. And this is, if you just plot the data, these are what it looks like. So there were players from Stoke, Spurs, and West Brom. And I believe this person who's tagged as West Brom was actually on loan from Spurs to West Brom at the time. So that kind of makes sense from that point of view. And if you fit our the clustering version of the latent shrinkage position model, it suggests 3 clusters and 2 dimensions. But again, you get this sort of one-shot single model that analyzes your data. So to conclude, this gives us a general Bayesian nonparametric approach that allows us to do dimension reduction, visualization for binary, and as I say in the paper, it's applied to count network data as well. The shrinkage prior very much borrows the work of Bhattacharya and Dunson, but allows us to intrinsically determine the number of effective dimensions that we actually need for the network. And we also developed a variational inference approach that allows fitting these models to much larger networks, so we don't have to rely on the slightly more laborious MCMC. And then, of course, there's a wealth of future extensions that we could do. Different networks, over dispersion is an issue in count networks. And again, this area of shrinkage priors has spawned a large volume of additional work. So there's very nice work on a related cumulative shrinkage process prior that would nicely kind of fit in here. To conclude, I'll just leave you with Gui's papers. The bulk of the work should appear in Bayesian analysis shortly. The variational inference approach was just last week accepted in STAT, which was a very fast turnaround journal. I'll highly recommend it, obviously because the work got accepted, but it was very quick in terms of the turnaround. And then the clustering paper is currently in preparation. So thanks again for the invitation. And as I say, this is work with Gui, Michael, and myself.
Thanks, Claire. So we do have the discussion section at the end, but if anyone has kind of a very specific question about this work, we probably have time for a question or two. I actually do have a question myself. I was wondering why it tends to perform better on kind of medium sparsity, medium density networks. The very sparse networks I can understand, but then the very dense networks, is it just that there is no real shrinkage to be had, or how does why do you think the model doesn't perform as well on very dense networks?
Yeah, good question. So yeah, with the sparse network, it's just harder there's less data in a sense to position the nodes. My intuition with the denser networks is it's sort of the same problem. There's so many possible, it's so dense, there's probably so many possible arrangements that you could have to generate that. That's a good question.
And I suppose, do most networks that you'd look at analyzing kind of hit that sweet spot anyway, just in terms of they're kind of probably the most interesting?
I think it depends on usually the context. So things, if you're looking at things like telecommunications networks and so on, unfortunately, no, usually they're very dense, and then they head towards the right-hand side of that plot. You know, smaller studies, you know, more typical in the, say, like that cat brain, for example, where it's a very focused study in a very focused region. Sometimes they are more in the happier place of densities. But I think that's very much kind of application specific.
Yeah, that makes sense that would be the case. So I suppose sparse ones are probably interesting in their own right, but much harder to deal with. If we don't have any more specific questions now, I'll thank Claire again for a very interesting talk. And we will have a further discussion at the end, but I'll hand over to Gabrielle now to introduce the next speaker.
Guys, thanks Amelia for the presentation. It's very interesting. Really enjoyed the presentation. Thank you.